Good morning friends. Today we are going to discuss about the MCQ question asked in good set. Up to the 2011 we discussed in earlier. Now today from we start 2012. The question is that work function of a metal is 1.6 electron volt is given, for which maximum wavelength the photoelectric emission is obtained. For a certain metal, the work function is given 1.6 electron volt. Whatever the maximum value of wavelength is required to produce the photoelectric emission. For that purpose, we know that work function phi is equal to HF is equal to Hc upon lambda. Therefore, lambda is equal to Hc upon phi. But here, work function is given in electron volt. We have to convert into joule. Therefore, Hc in upon E phi. It is substitute the value of constant, Planck's constant 6.6, 10 is to minus 34. Velocity of light in vacuum 3 into 10 is to 8 upon work function 1.6. Charge of an electron 1.6 into 10 is to minus 19. We obtain the value of wavelength, that is the 7734 angstrom. That means the 10 is to minus 10 meter is equal to 7734 angstrom. Again, we know that the equation of the work function phi is equal to HF, but we require the wavelength. Therefore, we convert the frequency into wavelength by substituting the F as C upon lambda. Therefore, Hc upon lambda. Therefore, lambda is equal to Hc upon phi. But work function is given in electron volt. We convert into joule. Therefore, we have to multiply by charge of an electron. Therefore, lambda is equal to Hc upon E. Substitute the value, we obtain the answer is 7734 angstrom. Okay. Next, asked in 2013, the kinetic energy of photoelectron emitted from a metals are K1 and K2. When it is irradiated with the light of wavelength lambda 1 and lambda 2, the work function of metal will be. Here the two kinds of the photoelectrons, or the photoelectrons with the two different kinetic energy are emitted. As the metal is illuminated by the light of wavelength lambda 1 and lambda 2. So what should be the work function of this given metal? For that purpose, we know that the equation, Einstein's photoelectric equation, kinetic energy is equal to HF minus phi. HF minus phi. Here we require the wavelength are given. Therefore, we can write is equal to Hc upon lambda minus phi. So from this equation, Hc upon lambda is equal to K plus phi. Take the phi on left hand side. Okay. Therefore, Hc is equal to K lambda plus phi lambda. Again, Hc upon lambda this side. Here the phi is taken on this side. Okay. Now, for wavelength lambda 1, the kinetic energy is K1. Right? Therefore, Hc is equal to K1 lambda 1 plus phi lambda 1. And for wavelength lambda 2, kinetic energy is K2. Therefore, Hc is equal to K2 lambda 2 plus phi lambda. Both equation, the left hand side are same of equation 1 and 2. Therefore, comparing these two equations, we obtain K1 lambda 1 plus phi lambda 1 is equal to K2 lambda 2 plus phi lambda 2. We require the value of phi wave function. Therefore, take this term on this side. Phi is taken common, lambda 2 minus lambda 1. Then K2 lambda 2 taken on left hand side. Therefore, K1 lambda 1 minus K2 lambda 2. Therefore, what function of a given metal phi? K1 lambda 1 minus K2 lambda 2 upon lambda 2 minus lambda 1. So that is our option A. K1 lambda 1 minus K2 lambda 2 upon lambda 2 minus lambda 1. Again here, the kinetic energy of photoelectrons emitted are given the K1 and K2. This kinetic energy associated with the light of wavelength lambda 1 and lambda 2 illuminated the metal. So what should be the work function of this metal? So from the Einstein's photoelectric equation, maximum kinetic energy is equal to HF minus phi. Here the wavelength are given, therefore the frequency f is converted into the wavelength, therefore phi is equal to, or kinetic energy is equal to Hc upon lambda minus phi. Therefore, Hc upon lambda is equal to K plus phi. Therefore, Hc is equal to K lambda plus phi lambda. For first case, the lambda 1 light is incident, kinetic energy is K1. Therefore, Hc is equal to K1 lambda 1 plus phi lambda 1. So, equation number 1. And then, Hc is equal to K2 lambda 2 plus phi lambda 2, equation 2. Left hand side of equation 1 and 2 are same. Comparing equation 1 and 2. Therefore, K1 lambda 1 plus lambda phi lambda 1 is equal to K2 lambda 2 plus phi lambda 2. Take the phi lambda 1 on the right hand side, phi common, lambda 2 minus lambda 1. And this term is on left hand side, therefore K1 lambda 1 minus K2 lambda 2. Thus, you obtain the wave function phi is equal to K1 lambda 1 minus K2 lambda 2 upon lambda 2 minus lambda 1. Now next, asked in 2013. A particle of mass m and charge q is accelerated through a voltage. Then de Broglie wavelength associated with it in meter is how much lambda? For that purpose, we know that the de Broglie wavelength lambda is equal to h upon p. P is the momentum. P is the momentum. Now we know that kinetic energy P square upon 2m is equal to Q into V. Is Q into V. Therefore, momentum P is equal to P square is equal to 2mQV. Therefore, P is equal to under root of 2mQV. Substitute here. Therefore, lambda is equal to h upon p. Value of the p is this 2mQV. Wavelength, de Broglie wavelength, lambda is equal to h upon under root of 2mQV. Again, the de Broglie wavelength lambda is equal to h upon p. But here, this charged particle having the mass m and charge q is accelerated by the voltage v. Therefore, p square upon 2m is equal to qv. Therefore, p is equal to under root of 2mqv. Is the momentum of the particle. Substitute here the value of p. Therefore, de Broglie wavelength lambda is equal to h upon under root of 2mqv. Okay. Now next. That is asked in 2013. That is the based on theory. Already we discussed when we discussed about the different type of the emission of electron. When a strong electric field of Hubble volt per meter is applied on the metal, the electric field electron is pulled out from the metal. that is the field emission of electron. If the high electric field is applied in a given region, the electrons are pulled out from this region or this material or this metal. So at that time, the minimum voltage per meter is required is 10:8 volt per meter. That is on the base of the theory. Therefore, answer is 10:8 volt per meter. Electric field is required. So that much strong electric field is sufficient to pull down the electron from the given metal. Okay. Now next, asked in 2014, if kinetic energy of emitted electron is made double, so its de Broglie wavelength will becomes how much? We makes the kinetic energy double. So what about the de Broglie wavelength? Now the kinetic energy K1 is equal to K. At that time the de Broglie wavelength is lambda 1. Now the kinetic energy becomes the double 2K. At that time what is the lambda? So we know that the de Broglie wavelength lambda is equal to h upon p. But momentum in terms of the kinetic energy 2mk. 2m. Therefore, lambda is equal to h upon under root of 2mk. Therefore, lambda proportional to the 1 upon k. Lambda proportional to the 1 upon under root of k. Therefore, lambda 2 upon lambda 1 is equal to under root of k1 upon k2 is equal to under root of k upon 2k is equal to 1 upon root 2 is equal to 1 upon root 2. Now again the de Broglie wavelength lambda is equal to h upon p. But momentum in terms of the kinetic energy is under root of 2mk. So from this equation, de Broglie wavelength lambda is equal to h upon under root of 2mk. Here the particle is same, electron is same, therefore the mass of electron is constant. Therefore wavelength is inversely proportional to the kinetic energy. Therefore lambda proportional to the 1 upon under root of k. Therefore lambda 2 upon lambda 1 is the ratio of under root of kinetic energy K1 initial to the final kinetic energy K2. Substitute the value. Initial is K, final is 2K, K cancel 1 upon root 2. Now after that, the threshold wavelength for lithium is 6250 angstrom. The wavelength of incident radiation required for photoelectric emission is. Now we know that for photoelectric emission, the condition is the threshold. The frequency of the incident radiation must be greater than or equal to its threshold frequency. It means the F greater than or is equal to F0. But here we have to derive this condition in terms of the wavelength. In terms of wavelength. Therefore, C upon lambda greater than or is equal to C upon lambda 0. Therefore, lambda must be less than or is equal to threshold wavelength. Wavelength required is less than or is equal to the threshold wavelength. Threshold wavelength for lithium is given to 6250 angstrom. Therefore, answer is the required wavelength is equal or less than 2650 angstrom. Now friends, the next question asked in 2014, object of 100 gram mass moves with velocity of 36 km per hour. The d Broglie wavelength associated with it will be. So now listen here, the mass and velocity are given. Mass is given the 100 gram, convert into kg, therefore 0.1 kg. Velocity is given in 36 km per hour, convert into meter per second. 36,000 kilometer, that is 1,000 meter, upon 1 hour is equal to 3600 seconds. Therefore 36 cancel, that cancel, therefore 10 meter per second. Therefore 10 meter per second. Now d Broglie wavelength lambda is equal to h upon p. P is the momentum, mass into velocity, h into upon mass into velocity. Substitute the value, lambda is equal to h, Planck's constant, upon mass 0.1 into velocity t. Therefore, there is the 6.63 into 10 is to minus 34. So lambda is in order of 10 is to minus 34 meter. 10 is to minus 34 meter. Because here the mass into velocity 0.1 into 10 becomes the 1. So what is the value of Planck's constant? That is the wavelength. Therefore the wavelength is in order of 10 is to minus 34 meter. Now next question asked in 2015. The d Broglie wavelength associated with a neutron of mass m and absolute temperature T is given by. Here the K is Boltzmann constant, not kinetic energy. We know that the kinetic energy half m v square is equal to 3 by 2 kT. K is Boltzmann constant. Now 2 to cancel, multiply both sides by m. Therefore, m square v square is equal to 3m kT. Take the square root, so that becomes the momentum. P is equal to mv is equal to under root of 3m kT. 3m kT. Now d Broglie wavelength lambda is equal to h upon p. Substitute the value of p. Therefore, h upon under root of 3m kT. Again, already we learned in 11th standard the average translational kinetic energy is equal to 3 by 2 kBT. kB, that means the Boltzmann constant. Here we denoted as only k. Therefore 3 by 2 kT. 2 to cancel. Multiply both sides by m. Therefore m square is equal to 3m kT. Now taking the square root, so we obtain the m into v. That is the momentum. Therefore momentum p is equal to mv is equal to under root of 3m kT. Now d Broglie wavelength lambda is equal to h upon momentum. Substitute the value of momentum p as under root of 3m kT. So there is your answer. D Broglie wavelength is equal to the h upon under root of 3m kT. 3m kT. After that, next question is most important. Asked 3 times, repeated. 2015, 17 and 19. 15, 17, 19. So for this year, there is also most important for 2021. Okay. Photons of energy 1 electron volt and 2.5 electron volt illuminated a metal whose work function is 0.5 electron volt. Right? Okay. So here the SF1 is given, there is the 1 electron volt. HF2 is given 2.5 electron volt. Work function is given the 0.5 electron volt. The ratio of maximum speed of emitted electrons is, we have to find out what is the ratio of the maximum speed of emitted electron. That means the V1 upon V2 we have to find out. Right? Therefore, the maximum kinetic energy, we know the equation of Einstein's photoelectric equation, half m v square is equal to hf minus phi. hf is the energy of incident radiation, phi is the work function, and half m v square maximum is the maximum kinetic energy of emitted photoelectrons. Now when the hf is 1 electron volt, therefore we have this equation for first case, V1 square is equal to HF1 minus phi. HF1 is given the 1 electron volt minus 0.5, that means the 0.5 electron volt. That is equation 1. Now for second case, half m V2 square is equal to HF2 minus phi. HF2 is given 2.5 minus work function 0.5, that means the 2 electron volt, equation 2. Thus we obtain the kinetic energy first case when the energy 1 electron volt is incident, at that time the maximum kinetic energy is 0.5 electron volt, half m V1 square. When the incident radiation having the energy is 2.5 electron volt, the maximum kinetic energy half m V2 square is equal to 2 electron volt. Taking the ratio of equation 1 and 2, therefore half m V1 square upon half m V2 square is equal to 0.5 upon 2 is equal to 1 by 4. So that is the ratio of maximum kinetic energy. We require the ratio of maximum speed, therefore taking the square root on both sides, therefore V1 upon V2 is equal to 1 by 2. The ratio of the maximum speed is 1 by 2. Clear? So this question is most important, and 3 times there is asked. So for this year there is also the probability to ask this numerical in objective and also the board exam. So easy, from Einstein's photoelectric equation, maximum kinetic energy is equal to hf minus phi. So when the energy hf is the incident energy is 1 electron volt, kinetic energy is half m V1 square, and when the incident energy is 2.5 electron volt HF2, at that time the maximum kinetic energy is half V2 square. Substitute here, take the ratio. So we obtain the ratio of the maximum kinetic energies is 1 by 4. But we require the ratio of the maximum speed of photoelectrons emitted, therefore V1 upon V2, we have to take the square root on both sides. We obtain the V1 upon V2 is equal to 1 by 2. Now, to change the de Broglie wavelength from 0.5 into 10 is to 10 meter to 1 into 10 is to minus 10 meter. That means we are making the de Broglie wavelength double. So its kinetic energy should be. So here the options are given. First we know that the de Broglie wavelength lambda is equal to h upon n is equal to h upon p. Now the momentum in terms of the kinetic energy is 2mt. is 2m. Substitute here. Therefore, lambda is equal to H upon under root of 2m. Under root of 2m. Therefore, lambda proportional to the 1 upon under root of. Therefore, K proportional to the, take the kinetic energy here, 1 upon lambda square. Therefore, K2 upon K1 is equal to lambda 1 square upon lambda 2 square. Now, the final kinetic energy to the initial kinetic energy is equal to lambda 1 square upon lambda 2 square. Right? Okay. Now, the lambda 1 is given 0.5 into 10 is to minus 10 whole square upon lambda 2 1 into 10 is to minus 10 whole square. 10 is to minus 10 cancel 0.5, that means the 1 by 2. So 1 by 2 square. Therefore, K2 upon K1 is equal to 1 by 4 and final kinetic energy is K1 by 4. Final kinetic energy is K1 by 4. That means the 1 by 4 times of its initial kinetic energy. Again, the de Broglie wavelength is changes from 0.5 to 10 is to 10 minus 10 meter to 1 into 10 is to minus 10 meter. Its kinetic energy should be. So we know that the de Broglie wavelength lambda is equal to h upon mp is equal to h upon p. Now, the momentum in terms of the kinetic energy is P is equal to under root of 2mk. Substitute here, lambda is equal to h upon under root of 2mk. Here the particle is same, that means the electron. Therefore, lambda is inversely proportional to the kinetic energy. Square root of kinetic energy. Therefore, K is equal to 1 upon lambda square. Therefore, K2 upon K1 is equal to lambda 1 square upon lambda 2 square. Here we substitute the value. So we obtain the K2 upon K1 is equal to 1 by 2 square. That means the 1 by 4, therefore K2 is equal to K1 by 4. Clear? After that, so this MCQ question also asked 2 times, 2016 and 19. Okay, now next is the threshold wavelength of sodium is 6,800 angstrom. So its work function is. Now we know that the work function phi is equal to HF0. Instead of the threshold frequency, here the threshold wavelength given is C upon lambda 0. It's C upon lambda 0. Now H is given as 6.6 into 10 is to minus 34. C, velocity of light in vacuum upon lambda 0, 6,800 angstrom. That means the 10 is to minus 10. So we obtain 2.9 2 into 10 is to minus 19 joule. Here we require the work function in joule. So here the threshold wavelength for sodium is given 6,800 angstrom. Its work function we have to find out in joule. So here we know that the equation of the work function phi is equal to HF0. Therefore HC upon lambda 0. Substitute the value of HC and lambda 0. We obtain 2.922 into 10 is to minus 19 joule. Now, next question asked in 2017 on the basis of the knowledge in discharge tube with the increase in number density of the gas, the intensity of the spectral line. Spectral line is also intensity of the spectral line is going to increase because as the number density of atoms in gas is increases, so emitted photoelectrons are also going to increase. Therefore, the intensity of spectral light obtained in photographic plate, it also becomes very sharp and high intensity. Therefore, the option is increases.